So, but this is really for an hour plus plus questions, right?
Right,
This is
right. Hour, 60 minutes, roughly, and then usually 15 minutes of questions, up to 15 minutes questions. We're pretty informal.
Okay.
Andy, can you hear us?
Oh, there he is.
Me?
Andy.
Yeah. Do we need to do anything about the recording?
Well, Sheldon has to click record at the moment that the talk starts. The YouTube is already on.
Right, but I made
Sheldon
Ron
be the host then?
Yeah. So yeah, if you could switch the host to me for safety, just to make sure I can do that. I think I can do it as co-host, but
Let's just make you host, and then you can make me co-host.
I can do that. Okay, and then here I am returning the favor. Okay. Okay, good.
Thank you.
You're welcome. Thank you. Okay, my watch says it's the top of the hour. Thomas, you ready to start? Okay.
Yes,
okay.
I am.
Okay, I'll go click record then. Okay, I'd like to welcome everybody to the Western Hemisphere Colloquium on Geometry and Physics. Today's speaker is Thomas Grimm, and he'll speak to us on the tameness of quantum physics. Oh, well, I'm sorry, let me interrupt 1 second. I didn't say an important thing. Is if there are questions, please feel free to unmute yourself and ask. Go ahead, Thomas.
Okay, well, first of all, thanks a lot for the invitation. It's a great pleasure to speak in this colloquium. And as was already mentioned, I will talk about the tameness of quantum physics. And this is based on a number of papers. There is one paper which I wrote in the end of 2021. And I should give a lot of credit to for the other works to my collaborators, brilliant collaborators, Mike Douglas and my postdoc Lawrence Schlechter, and 3 mathematicians who are all actually in the Western Hemisphere, very suitably for this colloquium, Benjamin Backer, Christian Schnell, and Jakob Zimmermann. So they are these are mathematicians. Okay, so now you see the title, but you might ask, what is this all about? So let me get started with some somewhat, let's say, not very controversial statement. I think it's fair to say that mathematics can be quite wild. In fact, if you think about your start of studies, either physics or mathematics, then one learns about topologies and maps. And in particular, in analysis, no mathematician will be hesitant to tell you the wildest construction you can imagine, just to make a case, right? That this is some counter example to consider. So let me just give some names which you have clearly heard. You have heard about complicated sets like Cantor sets, or complicated functions, for example, this function here, which is like 0 at the rational numbers and 1 at the irrational. That's a totally well-defined function. Or some function like the function f of x is equal to the sine over 1 of x. Sometimes this is called the topologist sine curve, Yeah, this is quite a it's quite a wild function. I try to draw it here. And why is it such a wild function? Actually, you cannot even say precisely what dimension the boundary of this function has, right? So it has, especially when it goes to 0, it has a really wild behavior. Now, one common feature to all these things is that there actually is no proper geometric representation. Yeah, even so, I kind of have drawn here some curve. It's actually a fake because I cannot really show you what is happening around 0. Now, if you go deeper into mathematics, actually things get even more wild, right? You maybe have heard about in logic of the incompleteness theorems, that certain statements are actually logically undecidable. Yeah. So, but as a physicist, you might, one might wonder that, or one might be convinced that physics is actually more tame. Yeah, that all these very wild phenomena should not appear in the actual physical world. Yeah. That's an easy to make statement, but what is much harder to do is to actually state what is a good tameness principle. So in order to kind of avoid these wild phenomena, what should we impose on physical situations such that they are absent? Now, I should mention a little bit how I got to this question. So as the title suggested, this talk will be quite far-reaching, but I originally came from a string theory perspective. And in fact, I entered the subject by thinking about finiteness questions. So I asked, I tried to think about the question if the number of physical theories which come out of string theory is actually finite. Okay. Now, you might say that maybe this finiteness is such a tameness principle. In fact, finiteness is something which especially theorists working on string theory have thought about for quite some time. It started as early as these works by Douglas and Acharya, but there has been much of recent activity thinking about finiteness of physical questions, like how many physical spectra of particles can come out of string theory, for example. What are the groups, the ranks of gauge groups which can come out of string theory? Now, the point which I want to make later on, in certain string theory models, finiteness is now part of a very general mathematical theorem. So despite kind of answering this long-standing question in a specific setting. Now, finiteness itself seems to be not a very nice criterion if you think about it, because it's more or less a yes or no criterion. You can say a discrete set has finitely many elements, yes or no. So that seems not very structural. So what one actually wants to do is one wants to find a structural criterion, ideally. And in fact, the way I got to learn about such a structural criterion, namely as proposed by tame geometry or omnimal geometry, exactly arose from this finiteness proof in which I mentioned here. So what is now this tameness principle, which is known for mathematics? So it implements a general finiteness principle. And how does it do it? It actually is a very basic statement, namely it restricts the allowed sets and the allowed functions which you can consider in your setting. Yeah, and you might call them tame sets and tame functions. It avoids wild sets and functions. So in particular, there are no infinite sets with infinitely many disconnected components. So integers and lattices and so on are not part of this tame world. In fact, it also forbids these functions which I mentioned before. Yeah, there are no functions which have infinitely many isolated minima, maxima, or zeros. And in fact, that means that this function sine of 1 over x is actually not allowed in this tame world. You know? Where does it originally come from? It actually studies. It comes from logic. Yeah, it's actually a concept which was developed by logicians, and maybe a rough motivation could be to say that what logicians wanted is they wanted to address certain old questions which were raised by Tarski about the decidability of certain systems. Yeah. So in fact, within these O-minimal structures, you have much better decidability properties in the questions in this point I raised before. Now, this is the logical motivation, or the motivation from the logic side, but there's another very beautiful motivation for this, namely this tameness principle actually gives a very nice way of introducing something which was called tame topology, and kind of satisfies the axioms or the ideas which were outlined in Grothendieck's sketch of a program. Yeah. And what was the idea there? Very roughly speaking, I think his vision was, so to say, to develop a mathematical topology which is made for geometers, not for people doing an analysis. You remember, that's where I started off with. Now, what is tameness more precisely? Tameness is built on the theory of O-minimal structures. It comes from model theory. There is an excellent introductory book by Van den Dries, and it's actually the nice thing about the subject is actually in its origin, it's very basic. It's very easy to understand the principles, the basic principles. That doesn't mean that it stops at being very basic. In fact, it's something which is researched very actively at the moment. And if you want to learn more, if you're not an expert in the subject and you want to learn more about the subject, there has been a very long 6 months field theory program. There are many talks, hundreds of talks on the subject, and also introductory lectures, and they all can be found online. Now, enough for the general talking. So what is this now? How is this defined? Yeah, I give you a rough definition, and if you work longer with this, you will see that it's a very natural definition. So the first thing which you introduce is a structure. So it's a very basic object, a structure, namely it's just a collection of subsets of Rn, but for every n equals 1, 2, and so on. Yeah. And now this collection of subsets of Rn, I want to make it closed under some very basic set theoretic operations. Yeah. So in particular, I want that finite union of sets in this collection, that they stay still in the collection, or finite intersections are still in the collection, or finite products of sets are still in this collection of sets, and the complements in this are still in this set. So this is very natural, and this has some analog in logic. So kind of unions and so on would be then a certain logical quantifier and or can be then represented geometrically. Now then there is something which is maybe not from the geometric point of view necessarily very obvious, but from logic point of view it is. We want to have this structure to be closed under linear projections. So if I pick out a direction, I want to make sure that if I project down by one coordinate, say, then the projected set is still part of this collection of subsets. Okay, and this is in logic. This corresponds to having the existential quantifier, like there exists an element of this type. Now, I add here another part of this definition. I want to have the structure to be sufficiently rich. Yeah, and what one can do is I want to include all the algebraic sets, which means all the sets defined by polynomial equations. Okay, otherwise all these axioms are just satisfied by the empty set. So then it becomes kind of a rich structure already. Now, this is what one calls a structure. Now the exciting thing now was that in the I think in the 80s, end 80s, beginning 90s, it was understood, I think, by Finiteness originally, that there is a very nice, simple condition how we can make the structure tame and remove some of these wild phenomena. And the way how to do that is by just constraining what are the allowed sets, the allowed subsets of the real line. And in fact, on the real line, all we want to have is finitely many points or intervals or unions of these. Okay, so this is the tameness axiom. This is the tameness condition. So that sounds very simple, but it turns out to be very powerful because of this projection condition, right? It means that when I have a higher dimensional set and I project somewhere linearly, whenever I project down to just a real line, I end up in this finite union of points and intervals. So just to give you a graphical representation, so you can have finitely many points or intervals of finite length, or you can have infinitely long intervals. They can be open or closed because you can always put the endpoints in the set as well. So this is the tameness condition. This is the tameness properties. Very seemingly simple properties, but with many remarkable implications. Now let me fix some language. This is not commonly used in mathematics, this language, but I find it extremely useful when talking about things. Now, I call the sets which are defined or which are part of this O-minimal structure. So the O-minimal structure is a structure satisfying this tameness property. I will call them tame sets. And functions with the graph being in a tame set, I will call a tame function. Okay. Now, if you understood what tame sets are, what tame functions are, then you can start to define what tame manifolds are by giving them some finite atlas and kind of making the transition functions between the set tame functions. And once you have done this, you have a full tame geometry. So I don't know, is there a question? There is a question, but I will answer this question in a moment. Okay, so now you have defined what one calls a tame geometry, and now let me give you a little bit more of a flavor. What is the right way to think about this, or how do you get a feeling for a tame function? So what I'm presenting you is one of the basic theorems in tame geometry. Namely, that if I consider a function f from the real line to the real line, then if it is a tame function, it always has the following feature. You can always split the domain of the function into finitely many intervals. You can like open intervals and you take out the endpoints here. And then you can show that on these open intervals, the function is either constant or monotonic and continuous. Okay, so the function can jump, but it can only jump finitely many times. Okay, and in between, it doesn't have maxima and minima, but it has only finitely many monotonic pieces. So this is in one dimension. And this is true for every tame function. So in particular, this implies that if the function is kind of nicely continuous, that it has only finitely many minima and maxima. And it also implies that when you go to infinity, there must be a last interval, right? Because you are only allowed to partition into finitely many intervals. And so there must always be a last interval, and this last interval on the real line will be infinitely long. And then something tame should happen there, because the function is not allowed to do anything anymore on this last interval. Okay, these are kind of how examples of tame functions look like. Yeah, of course, we have to show, first of all, that more precisely what they are. But let me give you some non-examples, which are pretty obvious if you compare it with this theorem here. Any periodic function, like a sine function on the real line, is not a tame function. Why? It has infinitely many maxima and minima. Now, here comes the question, or here comes the answer to question in the chat. Is there a unique O-minimal structure? Well, the answer is no. Otherwise, it probably would, well, maybe it would be exciting, but it turns out to be no. And in fact, the whole theory of O-minimal structures is very non-trivial, very non-trivial. Okay, so how do you construct examples of O-minimal structures? Well, you say which functions are allowed to generate your sets. Yeah, and this is very non-trivial to specify. So which functions are nice enough to generate such tame sets, such that if you project down to the real line, you only end up with intervals essentially, right? Now, what do I mean by this? So the simplest structure is called R-alg, and it contains the semi-algebraic sets. Yeah. So what do I mean by this? I mean that the sets which are generated as zeros of finitely many real polynomials. So you introduce some coordinates x1 to xn, and then the sets in this smallest O-minimal structure are just given by the polynomial equations equal to 0. And then because of this projection axiom, you also have to have inequalities. Okay. So this is the simplest setting. And now if you want to construct more involved O-minimal structures, you have to say which functions can I add to this. Namely, I take still my polynomials, but I allow now in these polynomial equations also other functions to appear. Like, think about the exponential function. You could just throw it into the game and ask, is the resulting structure still an O-minimal structure? Now, if you include just the equalities equal to 0, then you still have to make sure that all these axioms are satisfied. Okay, so this is quite non-trivial to construct these structures. And in fact, I think it's fair to say that this whole theory of O-minimal structures took off once the first, or once very non-trivial examples were constructed. Yeah, so a very influential theorem is by Wilkie from the mid-90s, where he showed that if you add the exponential function, then and with the exponential function, I mean the exponential function on the complete real line, that you can still preserve this O minimality axiom. Yeah. Of course, if you draw the function, it looks very tame, but the non-trivial part is that you have to make sure that this is true also in the higher dimension, if you use it to generate higher dimensional sets and have all these projection conditions. Now, interestingly, you can also introduce quite a large class of functions, namely the so-called restricted real analytic functions. So if you have an analytic function and you restrict it to a smaller interval and set it to 0 outside of this interval, so you have a function which is analytic on some large interval, and then you restrict it to a smaller interval, you throw it into this structure, and you still have O minimality preserved. In fact, you can do both things at once. You can include the restricted analytic function and the exponential function. Again, this is not a trivial statement. So kind of combining things is not, it's not obvious that O minimality is preserved, that tameness is preserved. And just to indicate that this is not something which was done in the 90s and it's kind of, it's all settled. Actually, this is still ongoing research, interesting research. So only last year, it was finally understood that you can find an O minimal structure which defines both the gamma function on this interval and the zeta functions. Yeah. So the study of O minimal structures is by no means a simple endeavor. Now, for R and X, just to kind of clarify this, you write down polynomial and polynomial equalities and inequalities, and in these polynomials, you can now use like these polynomial paths, the exponentials, and you can use these restricted analytic functions. Now, why is this structure particularly useful, as we will see later on? It is this structure which you need already if you want to define, if you want to make use of the complex exponential. Of course, the complex exponential cannot be defined on the complete complex line, but you have to restrict the angle because we know that there's a cosine and a sine appearing. But if you restrict cosine and sine, they are restricted analytic. Okay, so I gave you kind of maybe a somewhat standard introduction into O minimal structures and also a little bit of the history. And things came from logic, but I give you some maybe somewhat biased list of recent advances in the field. So this is a very active field. And in fact, O minimal structures or these tools have been used via some very non-trivial theorems to attack some long-standing conjectures. Yeah. And so it's a very active field connecting logic, number theory, and geometry. Okay, enough of the mathematics. Now you might ask, so I gave you now this little introduction into O minimal structures or some of the background. So now how do we see this in physics? Now I want to talk about quantum field theories, and I want to tell you essentially that what physicists have computed in these quantum field theories is actually part of such a tame structure. Now, so what does one compute in these quantum field theories? So one actually computes things which one can eventually measure, namely certain physical processes, for example, scattering of particles with certain momenta, and then one associates an amplitude to it, roughly speaking, how likely a certain process is. Now, in physics, one defines these amplitudes, or one definition is to use path integrals. Yeah, so this is some So of course, these are very complicated objects, so they are not necessarily very well defined from a mathematical perspective, but the idea one has is that one sums over all possible processes which are happening in such a scattering process. One way one could one way how physicists make process or how physicists evaluate these amplitudes is if you have a small parameter, then you can hope that you can compute these amplitudes by an expansion, some expansion, which is called the Feynman loop expansion. Yeah, and then you expand this, and you get like individual orders which contribute for a small parameter with smaller and smaller value to this amplitude. Oh, that's at least the hope. In reality, this is kind of not a convergent series, but that's the idea. Okay, and now what we were able to show actually is that for renormalizable quantum field theory with finitely many particles and interactions, actually all these finite loop amplitudes are in fact tame functions of the masses and the external momenta and the coupling constant. So I told you the external momenta are kind of the momenta of the particles you smash together, roughly speaking, and the coupling constant is like the strength of how these particles couple together. And you can, and the masses are the masses of particles, for example, which you have in your theory, and then they can appear in these Feynman diagrams. There's another question. Which notion of time? So in fact, what we have shown in this theorem is that they are definable in this O minimal structure R un exp. So it is really this very prominent O minimal structure, which is also used in most of these geometric applications. And I will tell you in a moment why this appears there. Okay, now this is quite exciting because it means that there is some sort of hidden finiteness property in all QFT amplitudes in this renormalizable theory, but it's not the finiteness you would imagine, but it's much more subtle. It's really in the structure of the functions which appear in these amplitudes. I should mention that the theorem is non-trivial, and in fact, it can have many interesting implications for Feynman amplitudes. So if one combines it with some of these recent advances in mathematics, one can hope that you can find new relation between symmetries of amplitudes and relations among them, like algebraic relations between amplitudes. Now, so why is it true, the statement? And you will see then also why the notion of tameness in this certain structure is relevant here. Well, first of all, you have to use that amplitudes are composed of finitely many Feynman integrals. So that's always very important. Finiteness, so tameness is preserved under finite addition. And every amplitude at fixed loop order can be represented by finitely many Feynman amplitudes or Feynman integrals, which are actual integrals. Now, Feynman integrals can now be related to, or it has been studied quite a bit how Feynman integrals can be related to period integrals. And that's probably something familiar to many of you. Period integrals are essentially integrals over certain cycles in manifolds. And what you can do is you can associate a kind of an auxiliary geometry to such a Feynman diagram. Okay, and then you are in the world of periods, And in the world of periods, there have been interesting advances recently. Namely, it was shown that such period integrals, or even more generally, period maps or mixed period maps even are tame maps. So they are definable in an O-minimal structure, namely in this O-minimal structure R unexp. Note that this is not quite as direct as it sounds, because in quantum field theories, there are singularities in this. So these are not just integrals which are immediately finite and so on. You actually have to do some procedures, some steps, namely you have to renormalize the theory by adding additional stuff to the theory. But the key point is that for this renormalizable theory, you only have to add finitely many counter terms, and tameness is preserved under finite operations. Okay, so that's that. In retrospect, that's a very nice motivation to think about tameness in physics, even though that's not how it started off with. But let's take this as a perspective. So now we have seen that kind of perturbative quantum field theory is tame, roughly speaking, at least at fixed loop order, at finite loop order. So what about the full quantum field theory? So I told you now in principle, one has to sum up infinitely many terms. And in principle, this is not a convergent series, that's some sort of trans series and so on. But it's in principle, you have to sum up the whole thing. And then the question would be, is the full result tame? No. So what do I mean by this precisely? Now we're looking at physical observables in a local quantum field theory. So if you're not familiar with this, let me just try to motivate it a little bit with some rather basic examples. So if you have a theory with a particle with a field, then it's defined by it can be defined by a Lagrangian, and a Lagrangian is just some sort of function of this field. But this Lagrangian can depend on parameters m and lambda in this case, and this is just the simplest example when one studies usually in physics. And these are just the parameters of the model. And now what one computes in the physical setting is correlation functions. So path integrals of operators. So these are just, if you want, local functions. So functions depending on some space-time position in some d-dimensional space-time. Here it's located at y1 to yk. And then this is a path integral over these operators, which you can think of as functions, but then there is a weight, and this weight is this integral over this Lagrangian. But it's an exponential weight. Yeah, so there's always an exponential weight appearing in these correlation functions. So this is a path integral, and there's an exponential weight. So now, what is now our question? We want to think about this in the following way. So physicists kind of know how to compute these things. This can be very complicated. They can be infinite. There might be procedures to remove infinities and so on. But the final answer, the physical answer at the end of the day, is some function. And this function depends on the space-time points, namely where I locate these operators, and it will depend on the parameters of your Lagrangian or of your theory. Yeah. So I just call all of them lambda. So this is now a complicated function on the product of space-time, sigma times sigma times sigma, and as many operators as you include, and the parameter space P. Okay. And now what we want to ask is, are these tame functions? Now, this is a very concrete question. The physical result at the end of the day, not the procedure. The procedure it's rather obviously not tame, how to compute them, right? So you have to do really involved things. Okay.
A question?
Yeah.
Can you permute the observables? Is the answer the correlation function symmetric under permutation?
So what one usually includes is some sort of ordering. So I suppressed some of these technical steps. So
the answer is no.
And the answer is no, but you can compute the time ordered. You can introduce some ordering if you want. So there's some natural ordering which you can use. But of course, if you want to use these things to kind of recover commutation relations of quantum physics, you can also do that. And then you have to distinguish the ordering.
Thank you.
I know this doesn't give you a satisfactory answer, but the whole theory behind this is quite involved to explain in a few words.
Right.
Okay. Now, but what we want to do, let me give the answer that for all I'm going to say, it's fine to permute things. Okay. So what I now want to do is I want to check a few simple examples where I can compute these path integrals, and you will see that it's a little bit of a cheap way out, because you will see that the examples which I present are very simple, right? Because these things are very complicated to compute. So what I want to compute these integrals where I do not introduce any operator. So these are just functions of these parameters, and these are then called partition functions. So in this case, you don't want to normalize everything to one. Okay, so now let's look at a few examples. Now we go into a 0D theory, and that means I just go to a point. So our space-time is just a point. That's admittedly physically very boring quantum field theory, but okay, you can do it. And what you find is, as the result of this, if you use the Sine-Gordon model, which is defined by a certain Lagrangian, you find a modified Bessel function now, and the exponential function. So what you actually see is that in this simple example, it's a physical theory, at least in higher dimensions, you find a tame function. So you can construct a period, and in fact, it's a tame function. Now, another physical example is the harmonic oscillator. There, for example, you can compute the finite temperature partition function. It's a very simple physical setting again. And what you find is that this partition function is given by the sinh, and sinh is just exponential functions. So exponentials are tame functions. So this is, again, a tame function. Now, going to a little bit more fancy setting, but still, it's still a more or less topological theory. If you go to two dimensions and you look at Young-Mills theory in 2 dimensions with pure Young-Mills, there's no particles charged, then what you find that the partition function is actually a theta function. And theta functions are, in fact, also tame functions on their fundamental domain, as shown in this paper. So that looks very promising. So at least in these simple examples, you see that there's only tame functions appear. Now in 2D theories, which applies in string theory, these sigma models, maybe you have heard about them, then you can compute the partition function on a 2-sphere. You see that it's given by periods again, and we know that periods are tame functions. Again, we have a 2-dimensional quantum field theory where the partition function is a tame function. In this case, a very non-trivial tame function, very, very non-trivial tame function. Now, to maybe a little bit disappointingly, let's go back to the example which I gave before, namely this phi to the 4 theory with this very simple Lagrangian or action in this case, and considered in 0 dimensions. And what you find if you compute the partition function here, you actually find a modified Bessel function again. But this is not, it's another Bessel function, so it's k1/4. And there you can ask, is this tame? Yeah, and so if you ask the mathematicians, well, first of all, we would expect that this is a tame function, but actually in this case, to my knowledge, and I of course I ask around, it's not known if this is a tame function. So this k1/4. It looks perfectly tame, but that's not how the story works. So showing tameness of a structure is a very, very non-trivial thing. And for these modified Bessel functions, this has not been shown. And in fact, the bigger question is, are exponential periods, as introduced by Kontsevich-Sake, for example, are these exponential periods tame functions? So while periods are tame, it's a normal period, as soon as you introduce exponentials in the integrals, it is not known if they are tame functions. So that's something for mathematicians to take on. In fact, there is a much broader question behind all of this. Namely, you can ask any 0-dimensional theory. So you take a quantum field theory on point. Then you just have ordinary integrals. And you can ask yourself, if I integrate some stuff which is tame, is the partition function a tame result? Yeah. And in fact, there is an old conjecture by Van den Dries and later by Kaiser, in fact, that if you have a real valued tame function, so in some O-minimal structure, then all the integrals, if you restrict to the sets where it's not infinite, this integral, then these are actually, again, tame functions. Okay. So this is an open conjecture. It's an open mathematics conjecture, and people are thinking actively about proving this, and this would be very useful for also for the exponential periods, obviously. Now, how open is this conjecture? First of all, it's not completely open in the sense that it has been shown for certain O-minimal structures. For example, if you put in this R unrestricted analytic, then the integrals are in R unexp. And it's not too surprising that the exponential appears here, because if you integrate 1 over x, then you get the logarithm, and then you are already in the exponential world. So you can start with something rational, a rational function, and you just already get exponentials or logarithms. But I have told you, and I stress this, that in the physical settings, there's always this exponential weight in the correlation functions. So actually what we want to integrate is the exponential. We want to have the exponential in the structure, which we integrate. And this is open. But if the mathematics conjecture is true, then starting from a tame set or from a set of tame observables, tame operators, sorry, which are tame functions on the fields, then or on the positions and the fields, then actually the integrals are tame functions again. Yeah, so if you assume that the Lagrangian is a tame function and that the operators are tame functions, then the integral should be a tame function again. So now you might ask, so does that mean that all QFTs are always tame? that every observable in a quantum field theory is tame? Well, the answer is no. And in fact, you can easily construct counterexamples. And from things which we know very well in physics, namely, if you have a discrete symmetry of infinite order, which you can implement in a quantum field theory with not too much effort, then this partition function here, so this kind of integral, which I introduced before, is actually never a tame function. It's like with the cosine, right? So they're like you have infinitely many copies of the fundamental period, so to say. So there's never a tame function. So tameness actually requires that such symmetries are absent. And this fits very well with some of the expectations or some of the statements we believe to know about quantum field theories which are compatible with quantum gravity. In fact, this is one of the best understood conjectures about quantum gravity, and it can be motivated from all sorts of angles, from black hole arguments, string theory, and so on, namely that such global symmetries should not exist in theories which are compatible with quantum gravity. Okay, very good. So so maybe there is already a first hint that tameness is not generally in a quantum field theory, but maybe in certain sets of quantum field theories. What is the dimension of it? So there's a question, what is the dimension of the discrete symmetry group? Well, the dimension of the discrete symmetry group is infinite, as I stated here. So it's really important that there are infinitely many images, right? Okay. Now, does that mean you cannot come up with non-tame quantum field theories if you get rid of the symmetries? No, unfortunately, fortunately, actually, it's not even as simple as that. So it's not that just if you get rid of symmetries, then everything is tame. In fact, you can easily write down things which are non-tame and do not have symmetries. So they are not covered by this conjecture here. Pick, for example, this. You just look at the function, in physical terms, a potential, a scalar potential, which consists of two cosines, but one has an irrational number appearing here. So this has no symmetry, so there is no period in it, because this is an irrational number, but still it's a non-tame function. And so this would be immediately out. Yeah. Such functions have never been constructed, for example, in string theory as a theory of quantum gravity. More recently, and maybe, well, as a fun example, let me put it like this, by Tachikawa, it was even constructed a theory which is just using a non-tame function. You see the sine function appearing here. It gives you a quantum field theory which has relatively easy to state undecidable statements, logically undecidable statements. But you see, the origin of this undecidability is the fact that there is this sine function appearing here. And if you minimize the sine function, you end up with the integers. And decidability, or these undecidability results, are always about the integers or some infinite discrete set. Tameness forbids these, right? So tameness depends on the UV origin of the theory. And therefore, one might ask if tameness is only something which comes in theories compatible with quantum gravity. And so you allow me, this last part is rather speculative, but I think it's something worthwhile thinking about. Namely, you think about it in the following way. Think of the set of all quantum field theories, which are some abstract set, very hard to classify. And then you say, well, maybe just a certain subset of these actually is compatible with quantum gravity, and only these are tame. So only these are defined by tame functions. Yeah. And in fact, this sort of perspective I formulated as a conjecture, namely that theories compatible with quantum gravity, if you want string theory, and if you fix the cutoff scale, all the theories below this are are labeled by a tame parameter space and have tame scalar field spaces and Lagrangians. So in some O-minimal structure. Now, the nice thing is this conjecture implies certain previous conjectures
Question?
about finiteness. Yes, sure.
Does the phrase consistently coupled to quantum gravity have a precise meaning?
No. In the sense that it has a precise meaning in the physical sense, right? You want to couple it to a quantized theory of gravity. But if you ask for a precise meaning from a mathematical perspective, this is my no, then this is not very precise. At least as of now, it's very hard to understand what such a theory, what are the features of this theory in general. We believe that string theory is such a theory of quantum gravity, and within string theory, you can test this conjecture. But as it's formulated now, this is a very broad conjecture. So that's why I meant that it's a speculative part. And I will make it hopefully up in the next part, which would be having some theorem. So having said this, this conjecture is, you can be viewing it as part of the swampland program, which is a program kind of quantifying honestly what we believe in forms of conjectures, what are universal constraints of quantum gravity. Yeah. So these are not claimed to be theorems. They are clearly marked as conjectures, and then you can test them within string theory, or you can use black hole arguments and so on. And as I already stressed, it's a bold conjecture. Yeah. So it's only based on evidence from string theory, and it fits nicely with some previous conjectures. Okay, so this is the conjecture. Now, clearly it's speculative, but we have some nice evidence for it. And the strongest evidence is actually this Tameness Theorem, which I mentioned already in the very beginning of the talk. So what is this Tameness Theorem? So now we are back in mathematics, but I want to motivate this mathematics with the physical setting, the string theory setting. So we actually study string theory settings in 10 or 12 dimensions. In this case, it will be a 12-dimensional theory. And in order to connect to 4 dimensions, some part of the space-time is on some compact manifold Y. And this compact manifold determines what's the physics in the 4-dimensional theory. Yeah. So the compact manifold determines what's the quantum field theory in the 4-dimensional space. And there is immediately a problem, which you might call the fifth force problem, namely if this manifold has deformations, then this would be immediately in contradiction with experiment. Okay, because these deformations of this manifold, if they are not protected by any physical potential, then they would lead to scalar fields, and that's a contradiction with fifth force experiments. Okay, and in the beginning 2000s, there was quite a lot of activity, and it's still ongoing, on what is called flux compactification. Okay, what is this flux compactification? Well, it essentially has the idea that I introduce an electromagnetic field, or some generalization thereof, in these compact dimensions. And then once you have this field, you cannot deform the space anymore, because something wants to wants to bind you to a certain configuration. Yeah, so there is kind of an energy barrier of changing this compact space. Now, mathematical terms, this electromagnetic field or generalized electromagnetic field is a 4-form on this manifold. And in fact, it lives in the 4th cohomology. So it lives really in the middle cohomology of this 8-dimensional manifold. And in fact, it's quantized. So it's actually an integral class in this 8-dimensional manifold. Okay. So now the idea is that the choice of this 4-form, this integral class, solves the 5th force problem. So it actually prevents you from doing deformations. But it seems like it introduces something which is very bad for tameness and finiteness. Namely, it lives on a lattice. And a lattice is very bad for tameness. So a lattice is never tame because it's an infinite discrete set. Now, let me quickly explain how this solves the 5th force problem. So the well-understood string theory solutions are where this Y4 is a Calabi-Yau manifold. So it's a Kähler manifold in particular. And then the solutions imply that because this is some kind of generalization of an electromagnetic field, there is some cancellation of charge going on. So this G4 actually has to satisfy this consistency condition. And in order to be a solution to this string theory setting or F theory setting, it has to satisfy this self-duality condition where the Hodge star on this integral class gives back the integral class. Yeah. And it has to be primitive, so it matches with the Kähler form on this Kähler manifold 0. Okay. And these conditions, they can be read as conditions on the choice of your deformation, on the choice of your complex structure. And if these fixes things to points, the locus where these conditions are satisfied are points, then you solve your 5th force problem. And now, how does finiteness and tameness come into the game? Well, I told you that these G4s live on a lattice. So now these conditions which I gave to you, if they still are only satisfied on the lattice, tameness is clearly absent from this. But there was a conjecture in the beginning of 2000s actually that there are only finitely many choices. And in fact, this is now a theorem if you fix the topology of this manifold. It's actually a much more general theorem than just on 8-dimensional manifolds, but in general. In fact, it generalizes a finiteness, a very famous theorem, or the finiteness part of a very famous theorem by Catani, Delin, and Kaplan about Hodge classes. So why does it do that? Well, remember the Hodge decomposition. If you have a Kähler manifold, you can always perform into PQ type a Hodge decomposition. And Hodge classes are the ones which are integral and are of type 2,2. But since we only want them to be self-dual, that means that we also allowed for 4,0 and 0,4 parts. And this Catani, Delin, Kaplan paper shows that the loci are complex algebraic. And here in this case, actually, the loci can even be real. Okay. And now the remarkable thing is that recently it was shown that the period map, which describes this PQ decomposition and how it changes with the complex structure, is actually a tame function. And it gave also a new proof of this famous theorem. And what one can now do is one can extend it to the self-dual setting. And in fact, in the self-dual setting, I think it's even more, you see even more the power of the whole thing, because there you're not anymore over the complex numbers, but everything is over the real numbers. So at the end of the day, there is a clear tameness theorem stating that in these effective theories, in the string theory setting, the parameter space, which are the choices of this this flux, are actually there are just finitely many choices. That's the interpretation of this. In fact, it says more. It says that the field space is a tame space as well. So if the locus are not points, then the locus is a tame space. It's actually undefinable. Okay, so I'm running over time. So let me just highlight in one or two slides quickly that you might say that kind of the string theory settings are very abstract and maybe it's very hard to show things in general. I think the remarkable thing is that this whole concept is so broad, and we believe it to be applicable in many parts of physics. And in particular, in CFTs, this would be an ideal testing ground for these tameness ideas. CFTs are very well defined, also mathematically well defined, and you can hope to actually prove things there. Yeah. And just to give you a rough idea, the idea is now that you actually associate to a set of physical theories a structure. Yeah. So for example, the structure in which the Lagrangians are defined and in which your space-time is defined. Okay. And you make it definable in some structure. Yeah. If you want logical structure. Just remember, this is this collection of sets, and you put all the things which you need in order to define your theory inside the structure. And to give you an example, if you have a polynomial Lagrangians or a space-time, which is just some standard thing like RD or some torus and so on, then this would be this algebraic structure, this R-alg of semi-algebraic sets. And then the idea is now throw in the physical observables into the structure, and you compute them, you compute all these partition functions, and then you have a new structure, namely the old structure plus these very non-trivial functions, these very, very non-trivial functions. And then for the harmonic oscillator, for example, what you get is Rexp, because you need the exponential, as I told you, right? Because you have to weight everything with the exponential. And then in logic, you could think about this in the following way. This structure should be rich enough to make all statements about your physical theory, to make them, like to formulate these statements. And then you can ask, when is this structure, if this starting structure is O minimal, is the structure where you throw in the physical observables, is this also O minimal? Or you can ask, what are the simple conditions on your set of theories such that this structure is O minimal? Yeah. And the tameness conjecture, which I provided before, is one example of such a statement for number 2. But now you can do that for all kinds of theories. So you could even try to do this for quantum gravity itself if you would have a proper definition of quantum gravity. But what we did in this recent paper is we did it for CFTs. But since I'm running short on time, I will just put it on the slide. Essentially, we said that in conformal field theories, which is a special set of quantum field theories which do not require a UV, a high energy completion, we actually expect tameness to be, if you want, omnipresent, okay? So you would say that all observables in such a CFT are tame functions. Now there are many known CFTs and many observables have been computed, so there is a huge set of data to test this conjecture. Yeah, and they are very non-trivial functions. So you can now throw me any CFT and I might not be able to tell you if it has been proved mathematically if these correlations functions are tame. Okay, let me skip this, and then you can ask, when is the set of conformal field theories itself tame? And then we gave very precise conditions on when this happens. So this is in 2 dimensions, there are certain conditions. And the most important condition in all these settings is always you have to restrict the degrees of freedom. Okay, so this brings me to the conclusion. So I suggested that tameness of the set of well-defined physical theories and say observables could be a new general principle, which is very interesting both from a physics side and also from a mathematics side to explore. I showed the tameness of perturbative quantum field theory amplitudes in certain non-perturbative settings. I gave evidence for tameness from effective theories arising in string theory. Namely, I showed you a new theorem about the self-duality of integral classes. In string theory, we would call this flux vacua. And, oh, sorry, this has already appeared now. We briefly discussed the tameness of conformal field theories and correlation functions. So this is in our recent paper, which appeared last Friday. So just to conclude, like with a sort of an anecdote, usually, I mean, it happens very often that students come to me, ask, so what mathematics courses should I take? And then the answer is, if you work on string theory, well, actually, almost all fields of mathematics are relevant if you do string theory or physics, a part of mathematical logic. Yeah. So that was, admittedly, I said this, and I think others said this as well. I think this talk maybe indicates that this was a mistake to say this. In fact, we now say that there is actually could be a very fruitful interaction, especially between the theory of O-minimal structures and sets of quantum field theory, observables in quantum field theory, but maybe observables in physics in general. And there's a lot of things left to explore at the interface of physics and mathematics, at this new interface, in particular implications of tameness, relations to other quantum gravity conjectures, and what I also find quite interesting, but this has been not explored to any extent, is kind of the connection with decidability, logical decidability. Thanks a lot, and sorry for running a little bit over time.
Hey, thanks, Jeremy, and thank you, Thomas, for an interesting talk. I see there's a question. You can just unmute yourself and just ask your question.
So one example of, I guess the most famous example of finiteness is there's supposed to be finitely many topologies of Calabi-Yaos of a given dimension. Is there any new information about that?
Can you repeat the question?
Yeah, so there is actually for this conjecture, this original conjecture by Douglas and Acharya, or for some of these finiteness conjectures, you want also the Calabi-Yau, the choices of Calabi-Yaus to be finite. And that would be actually then the tameness of the set of theories. And there is no one looked at this so far using these tameness techniques. So one thing which I think is very exciting and which we are thinking a little bit about is, you probably know this Cheeger's finiteness theorems. And it would be very nice to understand if one can find new proofs of these known theorems, known finiteness theorems in differential geometry. Differential geometry and topology using tame geometry. But would be, no one did this, so that would be very exciting. I don't know if this is possible. And eventually, it would be very nice if there is kind of a new approach to the finiteness of Calabi-Yau question using tame techniques. But there's no news on this, unfortunately. But it's kind of implied by some of these conjectures. So, or it's yeah.
So Lucas, you had your hand up. Could you unmute yourself and ask?
Do you hear me?
Yes, go ahead.
Thank you very much. And I have 2 comments and 1 question. Maybe I start with a question. My question is as follows: you have been talking, among others, about string theory. As a person who is standing outside string theory, because I'm dealing with rather classical field theory, solitons, skyrmions, and so forth, etc. I have such a question: what about the arguments of the opponents to the string theory? That this theory is very elegant, but it is a very elegant piece of mathematics, and this has not been confirmed experimentally. This is my question, and 2 comments. First comment is such that you have said, among others, that mathematics is wide. Mathematics can be more wide than we can imagine, and maybe you have heard about this. Maybe some group of Japanese mathematicians. This may be very, very strange, yes, but they have defined so-called division by zero. Division by zero, and it is the of Professor Saito, Kumura, etc. Because we know this very well, that nobody can divide by zero. Yes. However, they defined division independently on multiplication. So they obtained some interesting results, but this is 1 comment. And the second comment is such that you have mentioned about the among others mathematical logic. Mathematical logic suffers from a very serious problem, the problem of entailment problem, or relevance problem, which is connected to the problems of material implication. And this problem is very, in a nutshell, we can say that the problem is such that we have the implication, the conditional, if A, then B. So what is that? What does it mean? B entails from A. Many people have been trying to solve this problem, and in my opinion, in my personal opinion, the number of the people and the importance of this problem can be compared only to the problem of interpretation of quantum mechanics. So this is the problem that we have meet in mathematical logic paradoxes of material implication, and this causes the paradoxes in other branches of mathematics, arithmetic, topology, algebra, and so forth, which can be formalized by logic. This is my comment, and I
okay. So yeah, I
leave my website. And thank you.
I cannot say something about your comments, but well, if you someone standing outside of string theory, I think I understand that this might be seen as a mathematical construct, which is not experimentally confirmed, which is certainly true, and one has to be very modest about this. But I think it's also fair to say that this is one of our best understood candidates of a theory of quantum gravity, and this is also the way how I use it in this talk. So I didn't use it very much. I just used it to motivate certain conjectures, and I motivated a certain theorem. But yeah, this is our best personally, I think it's our best candidate, which we have of a theory of quantum gravity. And then, well, if you have such a candidate, use it. Try to learn something from it. And that's what we are doing. And it has been very successful over the last years for all kinds of applications. We have quite a few mathematicians in the audience, and it has influenced mathematics over many years. So, and that's also one part of my talk. I used it in this way as well, but I also used it to motivate some general conjectures.
Thanks. I see we're running out of time, but I did want to invite if there are other questions.
Yeah. So this is in the opposite direction of the previous question, which is I'm going to attack as the devil's advocate the mathematical formulation. Okay, I want to ask the devil's advocate question. So see, you use the real numbers as the basis of all the finite axioms. And already for me, the logic problems in mathematics start with, the completed integers creating the real numbers. I don't know. So, well, no, even before that, you might consider these minimal theories defined over the real numbers. Couldn't they also be defined over smaller fields contained in the real numbers, and then would sort of be equivalent? I mean, there'd be some theorems that say, I don't know, over certain algebraic extensions of Q that are totally real, that minimal structures defined that way would be roughly.
Yeah.
So that's the question. Yeah. So.
Yeah. So indeed, you can. You can do that, not over the real numbers. So if you look into, so I don't know from which side you are coming, but if you are looking in the original definitions of all minimal structures, you can do that over a certain field. Yeah, so you don't need to use the real numbers necessarily, and then you have to find a proper way of implementing tameness. So indeed, you can generalize.
You need a totally real field, so you can talk about positivity, right?
Exactly. You need an order.
Maybe.
Yes.
Yeah.
That's absolutely correct. So now, question: can you do it over p-adics or these sort of things? And then things get really tricky.
No, that's different. I mean, that's not like the reals because of the ordering, right? I mean.
Yes. But what I'm saying is, if you want to go even beyond this, then this developing this theory becomes challenging. These theories. Yeah.
No, but I'm suggesting there's something easy to say. You can just replace the real numbers by some fields that have the properties of the real numbers without considering all the real numbers. I'm suggesting something simple and easy.
No. What I'm saying is that the easy thing is done. I just didn't present it.
Yeah. Okay. So this is understood. Okay, fine. That's what okay.
So there's a much more general way of presenting this. I just put it to the real numbers.
Okay.
Saying,
that was just to make a concession to the audience. Okay.
So exactly. So this is.
No, but I mean, I love this fact that this is a good exercise if you don't know it, that any bijection of the real numbers, which preserves addition and multiplication, is the identity map. That's a nice exercise. And it uses exactly the things that you were using in your discussion. And this makes sense for more. There are no field automorphisms of the real numbers abstractly. The topology is intrinsic to the algebraic structure. And I love this fact. It's elementary and it's somehow implicitly in your discussion. But this is just a math comment on your discussion.
Yeah. No, and indeed. So in this logic way of introducing things, which I didn't describe at all, really, is you introduce the operations on the field, And if this field has an ordering, then you can take this as a starting point. And then many of these results can be mapped to the reals, and some others cannot. And then you have generalizations, and so it's much richer than I presented. But
Oh, okay.
Good.
Is there a reference about that?
well, you can, for example, you can look into Wilke's introduction to O minimality, and then he will. It's very short and it's very readable. It's just I don't know how many pages, 10 pages of introduction, and there at least the references are given. And also I would assume I think even in the
So what's the name?
Wilke.
Lukey? Oh,
Wilke.
Okay. Well, I'm going to I'm going to go just take the opportunity to stop the recording and thank Thomas again. I'll leave it on so we can have this informal discussion. But thank you once again for a great talk. And the next talk will be in 2 weeks. Will be Marcus Marino speaking on resurgence in non-perturbative topological groups. And thanks to everyone for coming. Okay. So I just want, because lots of people were dropping off, so I wanted people to hear me thank you again. That you can continue. I'm sorry to interrupt. But,
no, that's okay.
Yeah. Good.
I don't know if there are other questions or points of
there
discussion.
may be, but I just
well, I had one other comment. Okay, so I mean, I've been for decades been wondering about